In this video, we are going to talk about the position vector and the cylindrical system. This is our overview slide, which we will spend about 5 minutes on, and then we'll go through each of these topics in more detail and with more examples. The cylindrical system, the spherical system, which we will discuss in the next video, and the polar coordinate system are examples of curvilinear systems which differ in important ways from the Cartesian coordinate system, which we will discuss those differences. But because of the differences, we often draw position vectors associated with a point, not emanating from the origin, but at that point. The cylindrical system is composed of 3 coordinates, rho, phi, and z. And the first thing I'm going to warn you about, many places, I think most math textbooks, instead of a phi will put theta. But there are many places, I think mostly physics textbooks, well, they'll put phi here instead of theta. This isn't so much a problem here. It's sort of the same for spherical coordinates though, so that's where you really have to watch out. The phi and the theta are swapped. Anyway, so there are 3 coordinates, rho, phi, and z. Rho represents a length from the z-axis. Phi represents an angle from the x-axis, and then z represents a height from the xy plane. To convert from cylindrical to Cartesian, you use these equations. X equals rho cosine phi, y equals rho sine phi, and z equals z. And then to convert from Cartesian to cylindrical, you use rho equals square root of x squared plus y squared. Theta is inverse tangent of y over x, and z equals z. A couple of things again. The rho represents a distance from z, the z-axis, and also this theta needs to be between, by convention, negative pi over 2 and pi over 2. And we'll do a couple of examples, these very straightforward examples, and then a couple of other visual examples. And here is where we start talking about curvilinear systems and how they are different from the Cartesian system, and that is the unit basis vector Ez, E rho, and E phi. For the cylindrical coordinate system, each points in the direction that P moves when the corresponding coordinates is increased. So in other words, if you're at a point over here, maybe this is your point P, your basis vector for rho will point in the direction where rho increases. So from wherever you are, it'll point outwards. But notice if your point is over here, your basis vector then is going to point outwards from there. So you can see, depending on where you are, your basis vector for rho will change. Also for phi, so if this is your point here, and your phi goes from the x-axis over to this point, phi will then, your basis vector then points in the direction of increasing phi. And you can also see here, we'll do some examples, that E phi will depend on where your point is. Ez always points in the positive z direction, so that one stays constant. But the fact that the basis vectors depend on where you are in the space, or will change depending on where you are in the space, is what's different than from Cartesian coordinates. Last, we will take a brief look at polar coordinates, whose coordinates are rho and phi. It's essentially the 2-dimensional version of the cylindrical system where we stay in the xy plane, so z is equal to 0. And to convert from polar to Cartesian, we use this formula, x equals rho cosine phi, y equals rho sine phi. And then to convert from Cartesian to polar, we use the formulas rho equals x squared plus y squared, and phi equals inverse tangent of y over x. And now we are ready to go into more detail of our first topic, the position vector. We start with the position vector associated with the point P, and we denote that with r being position. It's a position vector, so we have a bar on top associated with point P, so r of P. So there's a position dependence of the curvilinear basis vectors that's not present in the Cartesian coordinates, and we had alluded to this in our introduction, that the basis vectors change according to where we are in the space. And for this reason, we sometimes draw a vector not emanating at the origin, but at that point. So here I have an example. Here I have our position vector, which is 2, 1. And then at this point 2, 1, we might have our first basis vector E1 that points in this direction and E2 that points in this direction here. I marked my point here in blue, and from what we were saying that we would do is we would make our vector RP not emanate at the origin as it is now, but at the point. So in other words, we're going to move this vector RP at the point. It's a little cluttered now because I have my basis vector also at this point, my two basis vectors. I cleaned up my drawing kind of by separating them into two pictures. So here is first my position vector emanating at the origin with the basis vectors drawn at the tip. And here I just moved my position vector up so it starts at that point. Now the next point is if we want to know the vector components, the components with respect to the basis, they're then obtained by projecting the vector onto the basis at that point. So it looks like to get the projection here, this E1 is going to have to be a little longer, E2 is going to be a little longer. So what I would get is, now I'm trying to draw this perpendicular to E2, this next line I'm going to try perpendicular to E1. So it looks like I need to multiply E1 by maybe another, 30, 40%, and E2 just needs to be multiplied by a smidgen more, and I will have my vector RP. So that's just getting the different vector components. Last, there are situations such as line integrals because the tip of the position vector follows the path of the integration. It's better to draw the vector emanating from the origin. So you don't want to throw this picture away completely. Just know that both are valid. In Cartesian coordinates, our position vector r is equal to r sub I, that is the ith coordinate, times e sub I hat, that is the ith basis vector. Also, we can write this with the x notation, x sub I, e sub I hat. And then we would say the coordinate, if we have 3 dimensions, r1, r2, r3. And formally, we would obtain r1 by multiplying, or dot multiplying the position vector r by the basis vector. To remind you how this works, let's say we have a position vector r, which is equal to r1 e1 plus r2 e2 plus r3 e3, as we have listed here in our summation formula. Then if we want to find r1, we do that by dot multiplying the position vector r by e1. So we're going to multiply r by e1, both sides of the equation. Here we have, we can distribute the dot, and also r1 is and r2, r3, they're just scalars, so we can pull them out. So we have r dot e1 is equal to r1 e1 dot e1, r2 dot e2 dot e1, and then r3 dot e3 dot e1. So here we have r dot e1. And now remember, if it's orthonormal, that means e1 and e2 dotted together gives you 0, and e3 dot e1 gives you 0, right? If they're 90 degrees, the dot product will equal to 0 because the dot product is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And if the cosine between them is 90, you get 0. So that leaves us with r dot e1 is equal to r e1 dot e1, which means our r1 coordinate will equal to r dot e1 over e1 dot e1. So this is how we find the different position vectors. Also, when we talked about projecting them onto the basis, this is what we're going to be using. And we're going to use this technique. It generalizes to any orthogonal coordinate system. And that's because the only thing we needed is when we dotted E1 with all the other bases vector that it goes to 0. In other words, E1 is orthogonal to the other bases vectors. And similarly for E2, you would dot R with E2. To find R3, you would dot R with E3. I wanted to give you a quick example of this, so I cleared out some space. I wrote my vector r in terms of r1 times e1 plus the second coordinate times the second basis vector plus the third coordinate times the third basis vector. And then I wrote, after we had done the dot product of this whole thing with e1 to get r1, that was r dot e1 over E1 dot E1. So as I said, I wanted to give you a quick example. And Cartesian coordinates, if I use the standard basis and I gave you the 0.21, that's just too easy because the first coordinate is 2 in the x direction and 1 is the first coordinate 1 in the y direction. By the way, I scaled this, so this is 1 and this is 2. So I had to come up with another basis, and this is the one I have right now, this E1 and E2. So I made E1 to be 1 over square root of 2, 1 over square root of 2, and E2 to be 1 over square root of 2 minus 1 over square root of 2. So essentially, they point in the direction 1, 1, and the direction 1, negative 1, but I wanted unit vectors, so I had to scale them with this 1 over square root of 2. I had to scale them by their length to make them unit length. And then I want to express this vector, 2, 1, in terms of my new bases. In other words, I want to find my coordinates r1, r2. When I multiply this together and add, I get 2, 1. And next, I did the same thing we did when we had this in the abstract. When I wanted to find the r1 coordinate, I multiplied both sides of the equation by the first basis vector. So that's what I have here. I didn't multiply, I did the dot product, sorry. So I have my left-hand side of the equation dotted with my first basis vector. And then over here I have the right-hand side of the equation also dotted with my first basis vector, but I can distribute. So I have this r1, my first vector, 1 over square root of 2, 1 over square root of 2, dotted with my first basis vector, 1 over square root of 2, 1 over square root of 2, plus r2, then I have this basis vector, 1 over square root of 2 minus 1 square root of 2, dotted with my first basis vector. The dot product just means we multiply by the transpose. So what you can see here is this, when we have the E2 dotted with E1, when you do the multiplication, this will go to 0. And that will leave us with R1 here is equal to this dot product, 2, 1 dotted with my 1 over square root of 2, 1 square root of 2, over the these two dotted together, which is just the magnitude of E1. So you know that's going to be dotted together and you're going to get 1. But you can dot them together and you can see it's equal to 1. So my final answer is 3 square root of 2. That's my first coordinate. And when I dot this equation here with E2, I'll get my second coordinate, R2, and that will be square root of 2. I feel like one of the things that makes me feel a lot better about these calculations is when I apply it to this graph here. So what I've said is that to get the 0.21, the first thing I need to do is scale E1 by a factor of 3 divided by square root of 2. So I'm scaling it by approximately a little more than 2, like 2.12. That's my blue vector here. So I basically took E1 and I more or less doubled the length and I added a tiny bit more. Then for R2, I need to scale my second basis vector by a factor of 1 over square root of 2, which is approximately 0.707. And that's what this blue line is over here. Now that I have scaled them, I can add these vectors together, which means I'm going to use the parallelogram law. Draw my little parallelogram. I didn't really quite scale it quite right, but you can see that if I had scaled it really well, I would have gotten the 0.21. So this is the 0.21 expressed in terms of coordinates of this new basis. And again, this technique is useful and we're going to generalize it to any orthogonal coordinate system, and we will be using it later. So that's what we have to say about position vector for now. So we'll go on to the cylindrical system. The cylindrical system represents a point in three-dimensional space with this triplet rho, phi, and z. So if you have this point here, let's project it down onto the xy plane for now, and the rho gives us the distance from the z-axis. The phi then is the angle that you need to make between the x-axis and our vector. And then finally, z is how much we need to move the point up along the z-axis. To convert from cylindrical to Cartesian coordinates, we let x equal rho cosine phi, y equals rho sine phi, and z equals z. And to convert from Cartesian to cylindrical, rho equals x squared plus y squared square rooted. Theta is equal to the inverse tangent yx, and theta must be, by convention, is between negative pi over 2 and pi over 2, and finally z is equal to z. You can derive these formulas for x and y, z is pretty easy, but you can derive these formulas for x and y by looking in the xy plane, so looking at z equals 0 when you look at x and y. Again, this phi is the angle between the x-axis and our vector, and then our vector has length of rho, so here we can see that the y is equal to rho sine phi and x is equal to rho cosine phi, and then you can also go backwards and see that rho is equal to x squared plus y squared, and that theta is inverse tangent of yx. You might just think of these as polar coordinates with the z coordinate added on. Also, we'll talk about this picture a little later. First, I want to do two really quick examples. First, to convert from Cartesian to cylindrical coordinates, the Cartesian coordinate 6, 6, 8. So here is Cartesian to cylindrical, so rho is equal to the square root of x squared plus y squared, so that gives us 6 square root of 2. Theta is equal to the inverse tangent of y over x, and we want theta to be between negative pi over 2 and pi over 2. So theta is the inverse tangent of y is 6 over x is 6, so that gives us pi over 4. And then z is equal to z, so 8. Z is equal to 8, so this is our solution. Next, to convert from cylindrical to Cartesian, we have 8, 2 pi over 3, negative 3. So cylindrical to Cartesian is over here. So x is going to be rho cosine phi. So x is 8, that's rho cosine 2 pi over 3, which will give us negative 4. Y is rho sine of phi, so y is equal to rho sine of 2 pi over 3, which is equal to 4 square root of 3, and then z is equal to z, so negative 3 is equal to negative 3. So this is our coordinate. And two more examples, just to make sure we kind of have the cylindrical system in our head. Graph and describe the surface expressed in cylindrical coordinates. Let a be a constant. So the first one is rho is equal to a constant. And the second one is phi is equal to a constant. So for rho is equal to a, that means we have a constant radius or distance from the z-axis. So it's kind of like this circle if we're just looking at z equals 0. But of course, we're not. We're in 3 dimensions. But the thing about this is for all values of z. So it's sort of like this circle just gets repeated all the way up the z-axis and actually all the way down the z-axis. So what we have is a cylinder. For our next example, we have phi, the angle from the x-axis, equals to some constant. So that's this here. And here, I have the vector stopping at the end of the page, but really it goes on to infinity because it's for all values of phi. And the other thing to note, we're not going to do negative values of rho because that would require a different value of phi. So far we've accounted for rho, which goes from 0 all the way out to infinity. We have phi, which is fixed, but z is not. So basically for every value of z, we have this repeated infinite ray. It's not a line, I guess it's an infinite ray. And what we end up with is this half plane, right? Because this goes out into infinity in this direction. It goes out into infinity in the z direction. But the thing is we don't go negative in the x direction. The next thing we're going to talk about are the unit bases vector, the unit bases in the z direction, the unit bases in the rho direction, and the unit basis in the phi direction. And the thing is, these bases vectors change depending where we are in the space. And the way we know what direction they point in is they point in the direction that our point moves in when the corresponding coordinate is increased. So looking at this, I have 2 points plotted for you. So here I have a rho, I have kind of a shallow phi, and then I have the small value for z. So our z direction is going to point in the direction that p moves when we increase z. So if we increase z, we're going to move up. So that's kind of easy. Then let's look at E rho. So if we increase rho, we're just going to keep following rho. So this is the direction that our basis vector for rho will point. And then finally for phi, if we increase phi, we're going to be going this way. So we kind of want phi to point towards that direction. We're going to talk more about what direction E phi points in exactly in a few minutes. And actually, it's probably the next thing I'm going to say after I finish this example. But let's compare that to this vector here. I have a much longer rho, a much bigger phi, and a bigger z. So at this point, z, if we want to increase in the z direction, we're going to go up just like this. However, if we want to point in the rho direction, now rho is going to be more out. So if you compare that to this row is more shallow. This one is more, what is the opposite of shallow? Whatever, unshallow. And then to increase phi, now we're going to be rotating around even more. And the important thing here is, unlike the Cartesian system, the cylindrical basis vectors are not fixed. As the point P moves, so like here we have one point P, here we have another point P, you notice that the bases for rho and the bases for phi also move. Z always points up. I want to take a closer look at these basis vector for EZ, E phi, and E rho. So I have my point here. So I have my z-axis, my x, my y. I've gone out rho from the z-axis, and then I've gone over phi radians from the x-axis, and then I go up z. So I kind of also made my little plane here. So here's rho, going out rho, and I'm up here at this height. So if I move from P in a little increasing direction in Z, I'm going to be going straight up. And that's always the case. If you want to move in the Z direction, in the positive direction, you're always going to go up. So this basis vector doesn't change. Let's look at the radial vector. So if I'm out here at P, one thing you'll notice about rho is you're always radially out from the z-axis. So this basis vector, if you're over here, then if you increase rho, you just kind of keep going in the same radial out direction and just larger rho. If you're over here, if your point P is over here, then you're pointing radially out, and you'll just keep going out this way. So this is the direction that your basis vector will point. You know, if you're down here in the plane and your rho is this way, of course, then your phi is only here. Then you're still pointing radially out, and your rho is this way. So you can see the basis vector for rho changes as according to where you are in the space. Now let's consider the basis vector for phi. So remember, phi kind of starts out at the x-axis at 0 degrees. And let's just draw our phi in here. Right. And then as we increase, we go up to pi over 2, we go to pi. When we get here back at the negative x-axis, we come to 3 pi over 2, and then we come to 2 pi. So what you see is our phi is kind of in this circle, which follows the circle, if we look at it, of the cylinder. So when we're out here at P, at this point, the basis vector for phi is in the direction that we're going over here. If we're back here, if our point is, if our point is over here, then our phi is going to point perpendicular this way, because this is the direction that we go, right, if we're increasing phi. If we're over here, then we kind of need to start going down, and then we'll come around this way. So phi just follows the circle. So one of the things you'll notice about phi and the basis vector for phi and the basis vector for rho, since rho is radially out and phi is perpendicular not perpendicular, is tangent to the circle, that will make the basis vector for phi and rho perpendicular to each other. And there's one other graph I wanted to show you because this is so weird. So here I have my two-dimensional space and I have my standard bases. So, the bases pointing in the x direction always points in the x direction. The bases for the y direction always points in the y direction. No matter where you are, you have this constant basis vector. That's what we mean when we say in the Cartesian coordinate system, the basis vectors are fixed, right? They always look like this, no matter what point you're at. Whereas here in the cylindrical, we said that our rho basis vector is always kind of radiating out. So that's what I have here, 3 of them at 3 different points. And then our phi vector is always perpendicular to rho and kind of increasing. So that's what I have here. I could add another one. Let's just say we're out here, I don't know, here. Well, we have to point radially out. So something like this, and then our phi would point something perpendicular. And perpendicular in a way that you think of like going in a circle. You're going this way, you're going further in a circle. You can imagine when you come up here, you're going further in a circle until finally you're pointing back up. I could do one more point. Let's just choose another point over here. This one's easy. I'm radially out as I increase rho, and I need to increase phi. And again, I think of increasing in the circle. So this is a drawing of my bases at different points in the xy plane. And then z, of course, the z basis is going straight up for each of these points. So the couple of notes, let's come back to this one in a minute. So first note, again, the basis vector for rho is always perpendicular to the basis vector for phi, and that the base, and also, the z vector is always pointing up, so it's also perpendicular. So this is, the basis vectors are orthonormal. So you can see when you dot them with the other basis vectors, they become 0. When you dot them with themselves, they become 1. And another point, notice if P lies exactly on the z-axis, so any point just on this axis, that the directions basis vector with respect to rho and with phi are undefined. Oh, and there's one other thing to say. The cylindrical coordinates, the rho, phi, and z, are a right-handed system. That is, if you align your right hand along rho and curl your fingers in the direction of phi, then your thumb will point in the direction of z. And then I also had this drawing over here that was the same as the cylindrical, but I also just wanted to draw the basis vector to remind you that the basis vector changes at every point. So it's common sometimes, although cluttery, I think, to draw the basis vector at each point as well. And now we've covered the cylindrical system, we'll have a quick word about the polar coordinates. And that is that the polar coordinates are sort of the two-dimensional analog of the cylindrical system. We just get rid of the z and say everything happens at z equals 0 in the xy plane. So to convert from polar to Cartesian, we have x equals rho cosine theta and y equals rho sine phi. I'm so used to this being a theta, but it's phi. And then Cartesian to polar, well, rho will equal to square root of x squared plus y squared, and phi is equal to inverse tangent of y over x. Here I have a drawing of our point P. So rho is the distance from the origin to P, and phi is our angle between the x-axis and our vector. And then we still have our basis vector, which we put at the point, our basis with respect to rho, and our basis with respect to phi. Another note, the position vector has only the rho component and is expressed as r is equal to rho times the basis vector. So here I have my point P, and I have my vector. My vector here, that can be expressed as both rho and phi, but once I want to express a position vector, I'll move my position vector here, so this will be r, and we express it only as rho and then with respect to p. And then this last drawing, just to remind you, if you have a vector, you can decompose it into some coordinate times your basis vector in the phi direction, and another coordinate times a basis vector in the rho direction. Essentially, you're scaling it. In this example, I'm scaling this to make it a little longer, this to make it a little longer. I add them together and I get my vector v, much like we did in that longer example for cylindrical coordinates. To review what we've covered in this video, we started with the position vector, and we also talked about how in curvilinear spaces, the bases will change according to where you are in this space. And for that reason, sometimes it's convenient to draw our position vector not with the origin, not emanating from the origin, but emanating from the point. Both representations are valid. And then we also talked about if we have an orthogonal basis, that we could get our coordinates for each basis vector by dot multiplying the position vector r by the basis vector if we wanted the first coordinate e1. If we want the ith coordinate, then e sub I. And we said we would use this technique to generalize to any orthogonal coordinate system. The next thing we talked about was the cylindrical system, which was the triplet rho, phi, and z. So it represents a point in three-dimensional space. Rho is the distance out from the z-axis, phi is the angle from the x-axis, and then z is the height from the xy plane. We have these formulas here to convert from cylindrical to Cartesian coordinates. X equals rho cosine phi, y equals rho sine phi, and z equals z. To convert from Cartesian to cylindrical, rho equals x squared plus y squared square rooted. Theta is equal to the inverse tan of y over x, where phi goes between negative pi over 2 and pi over 2, and z equals z. And all of these formulas here, or equations here, you can derive by looking at the trigonometry. Draw a picture and then do the trigonometry. And here I have, again, the point that's represented by rho, phi, and z. And then one of the things we said is because the basis vectors change depending on where we are in the three-dimensional space, we often draw the little set of basis vectors at the point as well. And we had this picture to show us what happens. So basically, the unit basis vectors, ez, e rho, and e phi, for the cylindrical system, each points in the direction that p moves when the corresponding coordinate is increased. So unlike the Cartesian system, the cylindrical basis vectors are not fixed. So we looked at that over here. Z isn't too bad because z always points up. So if you move the point p in the direction of increasing z, then you're always going to be moving up. However, if you're over here at this point and your rho looks like this, when you want to move the point to increase rho over here, that's going to be a different direction than if you're out over here. It could be the same length. It's just basically a different angle, because here, rho, you would need to move over in this direction. So rho, first of all, is always radially outwards because it's the distance from z. So it always measures radially outwards, but it'll change according to where you are in the space. And then second, we looked at the basis vector with respect to phi. So if you're over here and you want to move, you're kind of moving in this direction to increase phi, but if you're over here, you're going to move in a steeper angle. So depending where you are, phi will change. But one of the things we noted is phi always points along the circle because you're increasing the radians, right? Or you're basically increasing the angle. So it's always along the circle. It's tangent to the circle, which means that your basis vector for phi is always going to be perpendicular to your basis vector for rho, which is radially outwards. The last thing we looked at were polar coordinates, and we very briefly looked at it. Essentially, polar coordinates are the same as Cartesian or cylindrical coordinates without the z. In other words, it's the cylindrical coordinates in the xy plane. So we have the similar formulas: x equals rho cosine phi, and y equals rho sine phi. Z is just equal to 0. And then our Cartesian to polar, rho is equal square root of x squared plus y squared, and phi is the inverse tangent y over x with the same caveat. Phi goes between negative pi over 2 and pi over 2. So that's it for this video. Thank you for watching.